Okay, so let's start. I think most of the people already online. So today we have Professor Ingo Breunig from Freiburg University, and I would guess the talk will be about quadratic microresonators with quadratic nonlinearities.
Yes, yes, of course, of course.
Okay, okay, Ingo, you're welcome.
Okay. So then, welcome to everybody, and I will share my screen with you that you can see my slides. I hope it's going to work. Let's see. Okay, let's start in the beginning. Okay, here we go. I hope everybody can see my slides. So as Dimitri already indicated, the topic is of my webinar presentation is frequency conversion in microcavities made of non-centrosymmetric materials. So we are talking about quadratic nonlinearities here. And so I will start with some brief fundamentals, and then I will talk about three different kinds of frequency conversion. And the first one is optical parametric oscillation. Then I will talk about frequency comb generation in these non-centrosymmetric crystals. And finally, I will talk about adiabatic frequency conversion, which is not that explored yet, but let's see. I really, really like this way of frequency conversion. Okay, so we are talking today about non-centrosymmetric materials. What does it mean actually? So here on the left side, we have a picture or a drawing of the structure of lithium niobate, one of the most famous non-centrosymmetric materials. So in red, you have the oxygen ions. So in yellow, you have the lithium and the niobium in green. And if you look carefully, you will see that the niobium is always a little bit above the central point of this octahedron, and the lithium ions, they are a little bit ahead or on top of these oxygen planes. So that means the positive charges, they are not really centered around the negative ones and vice versa. So here then we have this sketch. So our negative charge, let's say it's an electron, sees an anharmonic potential. So it's not really centered between the two positive neighboring charges. And so that means in these crystals, if I force my electron to an oscillation by an oscillating electric field, my charge feels much more attracted here downwards to the positive charge that is closer. Right, so that means if you have an harmonic oscillation driving the electron or driving the displacement, the charge will do kind of an anharmonic oscillation. So, and this anharmonic oscillation can be described mathematically. So you have this displacement as a function of electric field. So you have the linear term as you would have it in centrosymmetric material. And the first nonlinear term is a quadratic one. And roughly 20% of all crystalline materials, they are non-centrosymmetric. So it's not very rare. And if you plot the displacement as a function of electric field, so for positive, in my picture now it's positive electric fields, your displacement x is a little bit lower compared with the displacement for negative electric fields. So if we come with an electric field that is an harmonic oscillation, just comprises one frequency component nu, and you bring this electron to oscillate, then you would see that the displacement is a little bit flattened at the top side here, right? And so if you Fourier transform this kind of strange function, then you will see that you get a DC term, which refers to optical rectification. Of course, you get something that oscillates with the frequency nu, and you get something additional that oscillates that at frequency 2 times nu. So you have basically second harmonic generation. And due to this anharmonic oscillation, you can have much more effects compared with not only optical rectification and optical second harmonic oscillation generation, you can have more. There is, for example, there is something that we call some frequency mixing. So you have two photons in the photon picture coming inside. So one with the angular frequency omega-1, one with the angular frequency omega-2. And at the output, you can generate just the photon having the sum frequency. And this relation between the input frequencies and the output frequencies can be interpreted as kind of an energy conservation, although it's a completely classical effect, right? So that's why I use, I would not strictly say that it's energy conservation. And if you have something like energy conservation, you have something that you can call momentum conservation. And this relates the propagation constants K of the incoming and the outgoing light. And here it's also like that the total momentum of the incoming photons is the momentum that we have on the output side, right? And the degenerate point or the degenerate process of some frequency generation is second harmonic generation. Here it's just like this, that the frequency of the two input photons is the same, right? And if you accept that you can combine two photons to a single one, to a larger one, then you might also accept that you can just put or input a large photon with a large frequency into the crystal, and then you basically split it. And this process is called optical parametric generation. And here we also can interpret this process with energy and momentum conservation. So these are two or three frequency mixing processes that are only available in non-centrosymmetric materials. And there is another one that is very, very important. It's the so-called Pockels effect. So here we take one of our non-centrosymmetric crystals and we just apply a voltage onto the top and bottom surface. So we generate an electric field inside, a static electric field. And let us assume that we have a light field with a certain amplitude. And let us, for simplicity, imagine that the amplitude of our light field is much weaker than the amplitude of the electric field or of our static electric field. So then our situation is like this. So we have the displacement of our electrons as a function of electric field. This curve, this red curve, is something that we already know from the previous slide. And if we apply an electric field, let's say like this, so it's the voltage divided by the distance of the electrodes. So then our electric field of the light field thinks or believes that it is in a centrosymmetric material having just the larger slope of this function x versus e, right, compared with this point around the zero here. And the slope is proportional to the refractive index, or the refractive index is proportional to the slope of this function. So that means the light field believes that it is in a material with a larger refractive index, right? If we go to positive electric fields to the other side, then our light field believes that it is in a material with a lower refractive index. So we can basically now plot the refractive index as a function of the static electric field, and it looks like this. So we just have a straight line. If we apply no electric field, then we have just the, the regular refractive index. And we can see that the refractive index can be varied just by applying a voltage. So, and if you do some math, then you will see that the refractive index change is just given by the cube of the refractive index times r. This is the Pockels coefficient times the electric field, our static electric field. So refractive index is proportional to the static electric field. Right. And just to give you an idea of orders of magnitude, if you have a refractive index of 2, you assume an R value and Pockels coefficient of 10 picometers per volt and a static electric field of 1 kilovolts per millimeter. So you get refractive index changes of the order of 10 to the power of -5, so to 10 to the power of -4. So this is typical, and we will use this effect later. We will need it for this adiabatic tuning. So please keep this in mind. So, and we want to use all these effects, so optical magnetic oscillation, second harmonic generation, and we want to use it in our optical whispering galleries. And so in our case, so most of our experiments, we are using this spheroidally shaped whispering galleries. They can have sizes between, let's say, some tens of micrometers until a millimeter in diameter. And they have quality factors up to 10 to the power of 10, which will give you roughly 10 kilometers effective path length. And in a millimeter size device, this will give us roughly 1 million round trips. And if you have 1 million round trips, you have a power enhancement of roughly 100,000. So which is quite a nice power enhancement. And this gives us the possibility to use the second order nonlinearity very, very efficiently. And the light field that is propagating in these spheroidally shaped resonators, it is characterized by these 3 mode numbers, M, P, and Q. And M gives us the number of oscillations in propagation direction. Q gives us the numbers of maxima in radial direction, and P gives us the 0 crossings in polar direction. So, and these transverse numbers, Q and P, they characterize the transverse mode structure and also the effective refractive index. And M gives us kind of, if you want to interpret it in the single photon picture, gives us the angular momentum of our light. So it is strictly connected to the propagation constant. Okay, so, and what do we need to take care of? Right, so energy conservation might be fulfilled. And then there is since we have a rotationally symmetric device, we do not fulfill momentum conservation. We will have to fulfill angular momentum conservation. So we need these 2 conservation laws. So here in with nu, we have the energy conservation. And as I told you, that M gives you just the angular momentum. We also have to fulfill angular momentum conservation. So the sum of the M numbers of the generated light, so it's the signal and the idler light that we are generating from the pump light. And so the sum of the M's of signal idler has to be exactly the M of the pump. And if you combine these 2 relations, then you see something pretty instructive. And the outcome is that the refractive index of the pump light, or the effective refractive index of the pump light, has to be the average value of the refractive index of signal and idler. And now let us have a look on the dependence of refractive index as a function of frequency. You will see it like this, right? So the largest frequency has the pump, and signal and idler, they have a lower frequency. So it means without doing anything, we cannot fulfill angular momentum conservation. It's just not possible, right? Because the refractive index of the pump is too high. So what can we do? So the first and most simple thing is use a birefringent material. So birefringent material means it's a material that has 2 refractive indices. So there is a certain axis that we call optical axis. And if your light polarization is parallel to the optic axis, then we have the extraordinary refractive index. And if the polarization is perpendicular to the optic axis, then we have the ordinary refractive index. So on the right-hand side, you see the refractive index as a function of wavelength. And if you have the pump having, for example, extraordinary polarization characterized by this E here, and Signet-Idler, they are ordinarily polarized, then the refractive index of the pump can indeed be the average value of the refractive indices of Signet-Idler, right? So, and in this situation, you can have phase matching or angular momentum conservation if you like to use the single photon picture. But what to do if your material is not birefringent, or you don't hit this, let's say, extraordinary point where your pump frequency is exactly such that you fulfill this condition, right? So then you can just accept that your refractive index is different, right? Of the pump is too high. This is something that we have to accept then. But we can then structure the material such that you have regions of positive nonlinearity and regions of negative nonlinearity. So what you do is basically you're inverting the crystalline structure, right? I will tell you later how we do this. So, and this gives you a certain periodicity, and this periodicity is given by the number capital M. In the single photon picture, you can think of it like you are creating an additional angular momentum, right? By this, by structuring this material, and then the whole angular momentum conservation law has to be, or this M has to be added to this conservation law, and then by changing or by choosing this M, you can just compensate any phase mismatch or any angular momentum mismatch. Okay, that's the idea. That's the most flexible way, because you can compensate any mismatch that you have if you are able to structure the material. But you need to structure the material. Okay. So, and let's see what we can do with this phase matching. So on the left-hand side, we will see an optical parametric oscillator that is phase matched birefringently. So here we pump in lithium, we consider lithium niobate as the material. The radius of the resonator is 1 millimeter, and we assume all three waves to be the fundamental, or to have the fundamental mode. So Q is 1 and P is 0. So then we pump at 332 nanometers, and our light polarization is extraordinary, and the light polarization of Signet-Idler is ordinary. So if we now calculate all the wavelengths that, or frequencies that fulfill energy and momentum or angular momentum conservation, we get this curve here, right? So since effective refractive index also depends on temperature, we can tune the frequencies that are generated on the output side. And in orange, you have the signal light, and in red, you have the corresponding Idler light. And you can see that you can go pretty close to the point of degeneracy here at, 87 degrees centigrade. And then you just increase the frequency distance of Signet-Idler by increasing the temperature. So you can have here a tuning between 900 nanometers and 1.3 micron roughly. So if you like to pump in the infrared, so at 1 micrometer wavelength, and you want to use the same polarizations for all output waves, which would give you the possibility to use the highest nonlinearity of this crystal, then, as I told you, you might need to compensate phase mismatch, and you can do this. You need a structure with 263 periods around the rim. And if you do this, then you can change the output wavelength just by changing the temperature from 50 to, roughly 95 degrees C. You can change the output wavelength from 1.9 to 2.3 micrometers. And of course, there are different curves for other mode number combinations, right? So you can choose the pump mode number, and then this curve will be shifted or somewhere else. So you can have not only the temperature as a tuning knob, you can also use the pump mode number as a tuning knob. Okay, that's the fundamental part. Now let's see how this is done in practice, or how does it really work. This is, so far it's just a piece of paper, right? So we draw something on it, and now let's see, compare it with reality. So first, let me explain you how we generate this quasi phase matching structure. And this is a fairly nice setup in our lab, and it's two PhD students, they really made it working very, very nicely. It was Christoph and Simon. And the idea is to use just a piece of lithium niobate, put a back electrode on this side, and then use a charged metal tip as kind of a pen, right? So it is called calligraphic poling. And just if you apply a negative voltage, let's look onto the structure of lithium niobate. And as I told you, the lithium and niobium ions, they are somehow not centered around their this oxygen planes here, or this inside this oxygen octahedron. And if you have the on top here a negatively charged tip, then you will pull the lithium into the second stable position, which is above this oxygen plane, or the niobium here on the higher side in this octahedron, right? So then you invert the structure where you have the charged metal tip, right? And the nice thing about this procedure is, if you come up with an idea in the morning, I want this structure, you can just draw it. And it takes you maybe, I don't know, half an hour, and then it's done. You don't need to buy it somewhere at a company and wait for 3 months and spend $3,500 without knowing whether it works, right? You come up with an idea, you do it, in half an hour you have the sample, and you can try whether your idea was good or not, or the idea of your supervisor, right? So the supervisor can now go to the students and say, okay, try it. And then let's see whether this idea was good or not. And most of the time it's not. So you don't need to waste any money. So here you see a picture of such a radial structure. On the left side, you see the full ring, and in red, I have indicated the light path for the light propagation, where it should be, right? So it has a radius here of 1.5 micron, and we choose a structure with 746 inverted lines. And here you have a zoom of this region here, and you can nicely see these parallel lines. And yeah, so this shows the flexibility. You can, if you like, you can draw your name into the structure. Okay, so we can generate these quasi-phase matching structures, and now we need to fabricate a resonator out of it. So how do we do this? So we take one of our crystals. It can comprise a phase matching structure or not, if we want to use birefringent phase matching. So then we take a femtosecond laser and we cut out a ring. So if we have this ring, we just glue it on top of kind of a brass post. This brass post with the ring is put into an air-bearing spindle. And here we have two options. We can rotate this air-bearing spindle and shape the rim with a diamond knife. It's the option here on the left side. Or we can use the same femtosecond laser and shape the rim with a femtosecond laser. And nowadays we are just using the option with the femtosecond laser. It gives us a higher reproducibility and a much better surface quality after the shaping process. And so then you have shaped the rim, and finally you need to polish the rim, really to get the surface roughness below 1 nanometer. So this is surface roughness we are happy with, to get quality factors, I don't know, beyond 10 to the power of 7, beyond 10 to the power of 8. Otherwise, we are pretty disappointed. So this is not a good resonator in our lab if we use lithium niobate. So the nice thing is that the polishing process does not really take long. So at least for lithium niobate, and if we use the femtosecond laser, it can be just a few minutes, and then this is done. So that means you're not screwing up the surface if you do it right. Okay, now we have our resonator. And how do they look like? And we have really used the scheme for various non-centrosymmetric crystals. And this is just a collection of them. We used, for example, barium magnesium fluoride, a brilliant crystal. It's transparent from 140 nanometers to 10 micrometers. So it's this purple bar here. It indicates the transparency range. And the nice thing is it is without a single resonance in between. So it's really, it has an ultraviolet edge here at 140 nanometers, and it has an infrared edge here at 10 micrometers and nothing in between. It's a very nice crystal. So we achieved a quality factor of 10 to the power of 7 with it. It was not so easy to work with it, but it worked. And then we have lithium tetraborate, also a very, very nice crystal. From point of quality factor, it gives us 10 to the power of 8, even here in the UV. So then we have our famous lithium niobate. We have potassium, tantalum, niobium crystals. This is crystals with very, very huge electro-optic coefficients. It has, you can generate refractive index changes orders of magnitude higher than in lithium niobate. If you operate it close to a certain phase transition, then you have zinc selenide, very nice crystal, transparent up to 20 micrometers. We have cadmium silicon phosphide, a nice, fairly new crystal for the infrared range. Orientation pattern gallium arsenide or non-pattern gallium phosphide, phosphide. And then fairly, yes, old-fashioned but very nice crystal, silver gallium selenide for the infrared. So this procedure, just by cutting and hand polishing at the end, works with basically everything that is solid. And this gives us very high flexibility in terms of wavelength ranges where we work on. Okay, so and the experimental setup, now we have the resonator, and the experimental setup is fairly simple, right? So we use a prism to couple our pump light into the resonator. Our pump lasers are, most of the times it's just some DFB lasers. So can be really, really compact. And so we generate signal and idler here in yellow and in red. We split off the pump light to see the pump transmission. And then we characterize the signal light and idler light with a spectrometer or with a power detector. So, and, you know, the presentation or the demonstration of the first OPO, it was basically, it was a race between two places. It was the Max Planck Institute for the Science of Light, so it's the place where Pascal went to, and the University of Bonn, so it was our group when we have been in Bonn, and it was the fight of the, let's say, the two schemes, right? It was birefringent phase matching versus quasi-phase matching. And the most simple one was used by the guys in Erlangen, and the most flexible one was used by our group. But the most simple one won the race, right? So they have been, I guess it was 2 months ahead of us. So they presented the first Whispering Gallery OPO in 2010, and we came later with our device at 2011. And the reason why, well, it was basically my fault, right? Because if you come from bulk cavity devices and you pump these bulk cavity devices at 1 micron, which I did in my PhD thesis, there is a strict rule. If you align it, you know, you always see the second harmonic of the pump light, which is green. And then if you carefully align these mirrors, and you will see that the green light turns to red. And the red light is just the second harmonic of the signal light. So And this is a rule for alignment of these OPOs. The green light will turn into red light. And if you don't see the red light, the OPO does not work. So and this is what I told the PhD student who did it. And I told him, before you see the red light, it makes no sense to put the detectors. The problem is that this additional second harmonic generation and or some frequency mixing does not happen necessarily, or only rarely happens, in whispering galleries. So there's a fundamental difference between the bow tie cavities and the whispering gallery, that these processes are very, very unlikely. So most probably the OPO was already running, and I told the PhD student not to put the detector because it makes no sense. So to all the PhD students out there, don't listen to your supervisor necessarily, right? So maybe we lost this race because of me. So, and as I told you, you can tune the output wavelengths of such an OPO just by changing the temperature and change the Q number, so the radial mode number of the pump. And here you see one example from our lab. So we have the wavelength, signal and idle wavelength here on the y-axis as a function of the temperature of our resonator. And just by changing the temperature from room temperature to maybe 90 degrees C, you can see two different curves. So the yellow one is achieved by Q pump equals 4, and Q pump equals 5 is given by the red curve. So we can just tune the output wavelengths between 1.7 and 2.7 micrometers, and we can even generate different shapes. And the solid lines, the nice thing is that the solid lines is not a fit, it's just a prediction of the model. So it does not comprise any strange fitting parameters. It was what we wanted. And to say truth, the region in the near infrared is fairly boring, right? At least for spectroscopy, right? If you want to do spectroscopy, you should go beyond 3 microns, something between 3 and 5 microns, right? To have a tunable device there, right? If you work in the infrared, you can basically have everything just from diode lasers in the near infrared. Story is different if you go to the mid infrared. So here we cannot use lithium niobate because the quality factor in the mid infrared is too low. So we are using, or we have used, cadmium silicon phosphide, and we pump it with a very compact diode laser operating in the telecom range. And also here we change the temperature between room temperature and 100 degrees C. And you can see various of these tuning curves. And these tuning curves are just also given by different pump mode numbers. So one pump mode number gives you the point of degeneracy here at 3 micron. Another pump numbers give you something that goes beyond 5 microns. So now here we have basically a tunable device that gives us output light tunable from 2.3 to 5.1 micrometer, basically without any gap. This is quite a nice device. So, and if you, let's say, collect all the tuning ranges of whispering gallery OPOs, right, then you will see if you pump, for example, lithium niobate devices in the blue, you can go even into the green region here to the near infrared. Then with cyan light, you have maybe some orangish or reddish light here on the low wavelength range. This is the green pumped OPO, so which is, or the 1 micron pumped OPO goes up to 2.7-ish micrometers. Then we have the cadmium silicon phosphide OPO. I presented it to you up to 5 micron. Then if you want to go beyond, let's say 6 micron, you cannot use cadmium silicon phosphide anymore. You should use a resonator made of, for example, silver gallium selenide. And here we were able to generate up to 9 micrometers wavelength just from a conventional diode laser. And here I really want to highlight one more experiment, not from our group, by a group in Yale, by Hong Tang's group. They have recently demonstrated a chip-integrated version of a second-order non-linearity-based parametric oscillator made of aluminum nitride, made of an aluminum nitride ring. They pumped it 800 nanometers, and they generated some tunable light around 1.6 micron wavelength. So these things can be integrated on a chip, so it's nice, very nice work. And one nice feature of these parametric oscillators is that they are really efficient. If you plot the conversion efficiency, or you look into the conversion efficiency, you might plot the output power versus the pump power. And on the left-hand side, I have plotted some data by Joseph Fürst. It was just the first demonstration of an whispering gallery OPO. And you can see that the threshold here was, I don't know, it was 20 microwatts. And already at 100 microwatts pump power, you have more than 20% conversion efficiency. So these devices are really efficient. And so then one of our PhD students, he improved the efficiency a bit. So he had a threshold of 2 milliwatts and he generated, I don't know, 5 milliwatts here. So he achieved efficiencies beyond 50%. So if the efficiency of a whispering gallery OPO does not be at, I don't know, at least 10%, then something is really, really wrong. Right, so this is something we would not consider parametric oscillation if it has no efficiency beyond 10% or something like that. Okay, so these devices are highly tunable. These devices are very efficient. Okay, now let's come to our second option, right? So frequency comb generation. Of course, this needs to be part of this presentation, right? It's a microcomb consortium. You want to know what about frequency combs here. So there are, let's say, two different concepts how to generate frequency combs via cascading second-order nonlinear processes. On the left-hand side, there is the process that starts with second harmonic generation, and on the right-hand side, we have the process that starts with optical parametric oscillation. Let's start with the second harmonic starting one. So we start at the higher frequency, at the lower frequency, the pump we have here. Right, on the left side, it's the blue component here, and we are generating second harmonic generation, this green light. And if the power of the green light exceeds the oscillation threshold of parametric oscillation, then you are generating sidebands. Right, and then these sidebands, they are converted to sidebands around the second harmonic, right, via some frequency mixing and via second harmonic generation. And then again, also there will be another cascade via difference frequency generation, so which increases the width of the comb around the pump. So we have basically generated now two combs, one centered around the pump and one centered around the second harmonic. And a similar concepts can be started, or similar cascade can be started if you start at the higher frequency. You have now the pump frequency here, and you are generating a signal and idler around the point of degeneracy here, so very close to the degeneracy. And if you exceed this threshold, then second harmonic generation and difference frequency generation, they start to form the combs centered around the pump and, let's say, the subharmonic, right? So these are the two concepts that can be used. And the one that is used most of the times is the one that starts with the second harmonic generation. And this is not something very, very new. In fact, it is more than almost 30 years old. So the first second harmonic OPO cascade was already observed in 1993. And it even was observed in monolithic resonators based on lithium niobate. it was not whispering galleries, right? It was devices like the one here on the left and the one here on the right. But here you already had a prism as a coupler. You launch the 1 micrometer pump light into it, and then you have 4 reflections, 4 total internal reflections on the right side and the bottom, on the left side, and on the top. And in this it was a monolithic resonator, totally based on total reflection. So it was very, very close already to whispering galleries. And the one on the right side was investigated in the same paper. It has just 3 reflections, and the circumference here for the light path was just 1 centimeter. So also very, very close to our scheme that we have today. And here you see the output spectrum around the pump. You see the pump light here in the central region. And if you launch just 400 microwatts into it, you see the sidebands just centered around the pump. So basically, this is the first rudimentary comb. But in 1993, nobody thought about the comb. And nobody even thought about the microcomb. But it was there. They just have not been aware of this effect. That the only thing that they just needed to do now is just increase the power. That's it. But they were just interested in how to tune the signal and how to tune signal and idler, just as in a conventional OPO, far away from degeneracy. Nobody cared about the operation at the point of degeneracy. But basically everything was already there in the early 90s. So, but then it took, 30 years almost, or no, it's 20 years, until this concept really was used to generate a frequency comb. It was done by an Italian group, so they had a mirror-based bow tie cavity. They have a periodically polar lithium niobate crystal as a frequency doubler. And on the left-hand side, you can see the second harmonic power is a function of pump power. The second harmonic power grows until a certain point, and then it saturates. And here you see that at this threshold point, then the power in the sidebands increased linearly. And here you see the output spectrum on the right side that they really generated around the pump at 1064 nanometers. They generated these sidebands. Right, so that was basically the first OPO driven by this second harmonic OPO cascade in a bow tie cavity. But even before this, a group from Finland, that's why I mentioned them here, they already had a similar comb, but used OPO as a first step. And with a second crystal for the second harmonic generation. So our idea was then to use this scheme in the whispering gallery. So Jan Sabados, PhD student in our group, he made a fairly nice experiment. He fabricated a resonator. Here you see the resonator and the greenish shiny rim. On the right side, you see the coupling prism. And so he launched some light at 1064 nanometers into the resonator. And on the output side, so here we used birefringent phase matching because of simplicity. And he characterized the output light with respect to power and spectrum. And one feature of this setup is that he could apply a voltage. And I told you that by using this Pockels effect, you can change the refractive index. So he could change the refractive index of the interacting waves such that he really optimized the interaction between the two waves. So really bringing both waves into resonance, so the second harmonic and also the pump. And so first at very, very low powers, considerably below 100 microwatts, he had observed the pump transmission as a function of pump detuning that looks nicely Lorentzian. And so he had a line width of 1.6 megahertz. This gives a quality factor around 10 to the power of 8, some 10 to the power of 8, so it was okay. And on the spectrum, he could just see the pump and the second harmonic. This is it. So then he increased the threshold, and beyond 100 microwatts, he already observed some sidebands around the pump and around the second harmonic. And if he increases, or then he increased the power to 2 milliwatts, then the situation was considerably different. The pump transmission was not Lorentzian anymore, right? It was deformed to this kind of triangular structure. And in this triangular structure, you see these kind of noisy regions. And if you go with the pump frequency there, let's say to this minus 40 megahertz, then you see an output spectrum that is visualized on the right-hand side. So you have a lot of several sidebands, and these sidebands, they are 20 free spectral ranges away from the pump. And you have the same structure in the second harmonic signal. So now if you stabilize your laser into this, say, second noisy region, here the situation looks a little bit different. Here you generate also a lot of sidebands, a lot of components, but here the distance between these components is 1 free spectral range. So you have a nice frequency comb, and you have it around the pump. Here we can resolve the lines. You can really see it here in the spectrum. And you see a broad continuous spectrum around the second harmonic, but this continuous spectrum is just due to the fact that we cannot resolve with this spectrometer the individual lines, but we believe they are there. So that's for frequency comb generation. Now let us talk about the third conversion process. It's the adiabatic tuning. And you know, if you have an introduction into whispering galleries, I guess most of you heard it, I don't know, roughly 100 times, that yes, whispering gallery resonator it's an effect coming from acoustics, right? That's what the name whispering indicates already. Also, adiabatic tuning comes from acoustics. So if you're looking on the left side where you are sitting, you might have a kind of an electric guitar, right? So you take your electric guitar, and what you can do is, okay, you're just getting kind of an F power chord. I hope everybody can hear it. And so you plug the F power chord, and you have a decay time of, I don't know, 5 to 10 seconds. So now during the decay time, you are sliding around the neck, right? So let's do it. Or vice versa. Okay, everybody knows this effect. And as we did it with the conventional whispering galleries, right? So we just convert this effect to optics. So let us use this effect and convert it to optics. So on the left-hand side, we have adiabatic frequency conversion with the guitar, right? What you have to do is you just change the length of the string during the decay time in seconds. Okay, the nice thing is it requires basically no nonlinearity, okay, except of the nonlinearity that is given in your amp, right, to distort the sound, to make it sound cool. You don't need high intensities at all. You don't need to take care of any phase matching. You just need fast changes of your string, or in optics, it's the resonator length. So if you convert this scheme to optics, it just tells us change the optical length of the cavity during the decay time. And the decay time in our case is something between nanoseconds to microseconds. And that's everything that we have to do. And the nice thing is, or one nice thing is, the efficiency is basically 100% because all the sound will go, let's say, from the F power chord to the high F power chord, right? There is no loss in energy. So let's do it. There are some approaches, some early approaches. And so the first one that was used is indicated here on the left side. It was femtosecond laser-induced charge injection. So you have your cavity and you might have a coupling waveguide and you have a control beam. This is the femtosecond laser pulse. And just by injecting charges, right, you change the refractive index. And since the pulse is so short, you can do it on a very, very tiny time scale. And here, the quality factor was 10 to the power of minus 10 to the power 4, and the guys achieved 300 gigahertz of tuning. This is quite a lot. The drawback is the quality factor is so low, but it has to be so low because you're injecting free charges, and free charges is never good for quality factor. And the same scheme was used not for just, let's say, ring or disc-like resonators, also for photonic crystal-based resonators. And one other drawback of this scheme is that you can only, increase the number of charges, right? That tells us that the frequency can be only changed to positive sides, right? You cannot just launch the pulse and remove charges. That is not going to happen. So then you can use the AC Kerr effect. So here you have a control beam, a strong continuous wave control beam, and this changes the refractive index and without any charges involved. That's why the quality factor was pretty high here. It was 10 to the power of 7. And the drawback here is that the tuning, the limit was of the order of 100 megahertz, so fairly low tuning. And the reason is that the AC Kerr effect is fairly weak. Then there have been also ideas to use electrically induced charge injection. Okay, it was not just an idea, the Japanese guys did it. But here also the cavity suffered from, in terms of quality factor, because you're injecting free charges. And then there is another paper, and here the guys induced some density changes via applying kind of a bias voltage. And due to this bias voltage, there was a metal stripe, and this metal stripe just increased in size and deformed the resonator. And here they could generate some 500 megahertz tuning. So when I brought this idea, I was a referee of a PhD thesis within this AC Kerr effect, using this AC Kerr effect scheme. I brought this idea back to our group, and then one PhD student said, okay, using the Pockels effect in our resonators, it should be fast. It should easily give us tunings of in the gigahertz range easily with just, I don't know, if you have 10 volts applied, and we could have quality factors beyond 10 to the power of 8. And okay, let's try it. So that was the idea, at least. So the idea is just to fabricate a resonator with 2 electrodes. And so the tuning, the frequency tuning, and adiabatic tuning is just given by this simple expression. So basically is the relative frequency change is just given by the relative refractive index change. And the refractive index change is given by this Pockels relation. So you just plug the second equation into the first one, and you see that the tuning just depends linearly on the applied electric field. And this is nice, right? To control something just with the voltage, and that the effect is proportional strictly proportional to just an electric field. And this tells us that we can basically generate arbitrary waveforms. Right? We just need to change the voltage. And the scheme looks as follows. So on the right-hand side, on the top side, we launch a light from our pump laser into the resonator. It circles around, and on the output side, we have two beams. One is reflected from the prism base, and the other one is just coming from the resonator. These two beams have the same frequency, they interfere, and depending on the phase relation between them, you get certain, maybe if you are at resonance, you get a drop in intensity. Right, so that's it. So if we apply a voltage fairly quickly, then the frequency of the light in the resonator changes. That means our detector now sees two frequencies. It sees the pump that is now not coupled anymore into the resonator because we shift our resonance frequency. And furthermore, it sees the light that comes out of the resonator but having a different frequency. And these two components, they form a beat signal that decays with the decay time of the cavity. So that's the idea. So if you observe this ring down here, this oscillation, this beat signal, then you know you have just converted the frequency of the internal resonator internal light. So, and this was Yannick and Louis who did this experiment. They have just used a laser at 1 micrometer wavelength and just applied 1 volt, and the resonator had a thickness of 300 micrometers. And on the right hand side you can see the in blue here, this voltage is switched on the nanosecond time scale, and then they observe the beat signal on the detector, and this distance between two maxima, so it's this 60 nanoseconds, it tells us, okay, it was a frequency shift of 16 megahertz. That's it. And you see a nice exponential decay, which also indicates a quality factor beyond 10 to the power of 8. Okay, and now we can just increase the voltage from 1 volt to 20 volts. So that's it. So same experiment, just increasing the pump. And you can see that as we expected, the frequency shift just grows linearly with the voltage. And one feature of this experiment was, in order to increase the electric field, we just decreased the thickness of the resonator, so the thickness D, right? We reduced it to 70 microns, and still it worked. So we could have 5 gigahertz, more than 5 gigahertz, just by applying 20 volts. And, let me go back here. Let me go back. Yeah, here on this, here you see something else, right? So one thing is that the frequency tuning is proportional to the electric field. Okay, we confirmed this. And it also tells us the frequency shift should be larger if the frequency is higher, right? And we wanted to confirm this as well. And it is really like expected, right? So we tried this scheme with 800 nanometers pump wavelength and also with 1.5, so in a telecom range. And you see that in the infrared, if you're using infrared light, the tuning is a little bit lower compared with the almost visible light at 800 nanometers. And the nice thing is that the straight lines, they are not just, fits, it's really the prediction that we had. And this prediction even assumes just the plate capacitor. Okay, and so how flexible the scheme is indicates the following measurement. During the decay time, say the decay time is of the order of, I don't know, 100 nanoseconds or some 100 nanoseconds, we just ramped the voltage up, to 20 volts, up to, I don't know, 25 nanoseconds, and then we ramped it down until 50 nanoseconds. And what you should observe here in the beat signal is kind of a chirp, right? So that your frequency shift here in the beginning part is low and is high here in the central part. And you can really see this, between these two maxima here to this initial maxima, the distance is roughly, or indicates a shift of 300 megahertz, and here in the central part is 1 gigahertz. So basically you can determine the frequency shift as you like it. You can have strange waveforms if you like. So it's basically just depends on your imagination, what you can do. Okay, this is basically it. So let me summarize. So if you're using non-centrosymmetric crystals, right, you have huge possibilities of frequency changes, right? You can just have widely tunable and efficient light sources. So it's just single frequency on the output side. They are very, very efficient. And it's just 1 millimeter in diameter. Then you can have broadband output. You can have frequency combs, right? It's just the same material, but under different conditions. You can generate frequency combs, even in the visible, or in hopefully in a few weeks in the mid-infrared. So Nicolas, one of our ESR in this consortium, is going to do this. And so you can also have this adiabatic frequency tuning where you very, very quickly change the frequency, right? So it's not really continuous wave anymore, but you can change the frequency on a nanosecond level. Okay, so this is it from my side, and I'm happy to answer your questions if you have some.
Thank you very much, Inga. This was absolutely fantastic. And questions from the consortium, please. Very interesting talk. There must be very interesting questions as well. I don't see. Yeah.
I have a question about a few slides back when you showed the parallel plate capacitor, where you could make the shifts. Yes, this plot.
Yeah.
Is there a reason why you cannot go to higher voltages for the 800 nanometer?
Okay. Since Luis is now in your lab, he can answer you the question. No. There was some stupid mistake or not mistake. There was something just not working in on the experiment.
All right.
And it was just okay. Do we want to stop here, or do we want to for some replacement, or yeah. It was no fundamental problem. This is something that annoys me every time when I show this graph. Yes, but there's no reason. So and 2 weeks ago, I told the PhD student, your first thing will to measure these points. So because it's just annoying to see this.
All right. Yeah. Thank you.
Yeah.
So if you feel more comfortable, then just raise your hand on the toolbar so that I can invite you with your question.
I think Toby posed a question in the chat.
Thanks, Joanna. So there is a question in the chat from Toby. Would it be possible to fabricate Ki2 resonators on chip?
Yes, of course. Oh, of course it is. There are several groups doing it. There are very, very good results on resonators made of lithium niobate with quality factors up to 10 to the power of 7. There is Paul Seidler from our consortium doing very nice stuff in gallium phosphide. I guess the quality factors are also beyond 10 to the power of 6 at least. I guess also approaching 10 to the power of 7.
In the gallium phosphide microresonators, no, we're not quite to 10 to the 6 yet. We're just a little bit under 10 to the 6.
Okay. Thank you. But there are and very good work from Hong Tang's group with the on-chip OPO. They have aluminum nitride rings, single crystalline ones now with Chi2 nonlinearity with quality factors beyond 10 to the power of 7. And they are, I guess it's currently under review. They have it put it onto the archive. They have a frequency comb there, also on chip based on second order nonlinearity. Although there might be a strong influence of Chi3, but there is something.
Yeah, more questions, please. So Ingo, what do you think about this Chi2 versus Chi3 competition? Well, in your devices or in some of your devices, is it important, or when can it be important, and should we care about it altogether or not?
Yeah, you know, in the experiment we had so far, you know, we pumped at in the green, and also our generated light, or no, we did not pump in the green. So, but we pumped at 1 micron and generated green light. So both waves, both combs were centered around wavelengths in the normal dispersion range. So it's very unlikely that in this range Chi3 will have a strong contribution, right? Because it's very, very much in the normal dispersion range. But if we would pump or would have our interacting waves in the anormal dispersion range, or close to 0 dispersion, I'm pretty sure that Chi3 will have a strong influence.
Mm.
And I know that at least from the archive paper from Hong Tang's group, they have deliberately set the dispersion such that pump and OPO light, they are in the normal dispersion range, and they see a soliton. But there is a strong, so at least from the graphs, I would assume that there's a strong influence of Chi3.
Mm-hmm. Okay, so we have a question from Xuan Go or why? What is the reason for calling adiabatic frequency conversion?
What is the reason?
Yeah, what is the reason for using adiabatic word in the name of frequency conversion?
Okay, yeah. So the name adiabatic frequency conversion was used first by a Japanese group, and you know, I understand it. I discussed it, why they gave it the name, and they said that, you know, a frequency, you know, you are not allowed to be too fast. You know, you should be faster than the decay time of the cavity, but you should not be much faster than the round trip time. If you are faster than the round trip time, then you might generate sidebands. Then you are losing this condition of adiabatic tuning. So then in this case, then the output light cannot really follow the change of the cavity length anymore. And from this perspective, they call it adiabatic if you are, let's say, not too fast. But you can be very, very fast. You can be infinitely fast if you fulfill some, you know, you always have to fulfill energy and angular momentum conservation, and you can get rid of the sidebands if you don't fulfill angular momentum conservation there on this side. So you can be very, very fast. Yeah, but you should not be too fast. So.
Okay, we have a question from Alexander Tusnin.
Yeah, thank you so much for your talk. I have a question about one of your last papers, a theoretical one in collaboration with Podivillov and Smirnov about nonlinear solitons in K2 materials. Do you have any experimental evidence now of observing such solitons?
No, not yet. So we, if you have a bunch of PhD students, just send it. You know, this is currently, you know, there are a lot of predictions, a lot of very, very interesting predictions, but it's just too few PhD students who can do the work. Yeah.
Okay, thank you. And what is main experimental difficulty in this case you expect to have?
I personally, I don't see a huge problem. You know, this frequency comb setup works every day. And it's really, we brought it from one lab to the other one, we switched it on and it still works. But we know that there are some guys who really suffer to see these combs, and I cannot really tell you what's the problem on this site. So if somebody is interested, please come to our lab and have a look and learn it. And you know, there's so much stuff currently, so much stuff is predicted. It's much more than we could do.
Okay, thank you so much.
Okay.
So do we have more questions? Yeah, if there are no more questions, I don't see any at the moment. Then let's thank Ingo again for a very nice talk and for answering all your questions, which have been very interesting as well. And so this is our last webinar before we sort of go on a consortium holiday, and then we're going to reassemble for webinars and training activities back in September. And if you have anything in between, please get in touch with me and Joanna as well. Yeah, thank you very much then, everybody, and have a good break.